Okay, so how about the output resistance? We're going to do that. We're going to calculate the output resistance in 2 steps. So number one is, or two different cases, for 2 different cases. So number one is without early effect, and then next slide we're going to do it with the early effect. So without the early effect, the circuit that I'm going to be dealing with looks like this, or well, more like this. There's no R0. So, and then I've turned off the input source. So here's ground. And I've applied this test voltage Vx and the Ix. Okay. Now I have to find the relation between Vx and Ix. What I'm gonna do here is that I'm gonna write a KVL in this path, and I'm gonna show you that it's gonna be very kind of useful for us for finding the relationship between Vx and Ix. So if I write the KVL, I notice that 0 minus V pi minus VRE is equal to 0, right? And then this means that negative V pi minus, and then instead of VRE, I'm going to write RE times IE. And instead of IE, I'm going to write V pi over R pi plus GM V pi. Since we have done this a few times up to now, I'm not going to basically redo this again. I'm not going to write all the steps. This is equal to 0, and then this means that V pi times negative 1 minus RE times 1 over R pi plus GM is going to be 0. What can I say about this? Well, I know that I have a current, so my GM is not going to be 0. My R pi is not going to be 0 because that's beta over GM. RE is a resistance, that's not going to be 0. And 1 is not going to be 0. So this expression tells me that my V pi is 0. And that's important because the moment I know V pi is 0, then I know that GM V pi is going to be 0. Therefore, this current source goes away. Therefore, my circuit is going to be simplified to this. So therefore, R out, which is equal to Vx over Ix, is just going to be RC. Okay, so in terms of R out, normal common emitter and common emitter with degeneration, they don't have any kind of difference, at least when there's no early effect. Okay, so they both have the same RC. So I did all of these stuff to tell you that when there is no early effect, V pi is going to be 0. So you're going to have to you are dealing with the same circuit that you dealt with when you were working with normal common emitter stage. So now if you want to find the output resistance or output impedance with the early effect, this is what we need to do. Again, I have the same small signal circuit. This time I've actually added this R0. And now I have to actually do the analysis. To do this analysis, I'm going to do a few tricks to make it a little bit simpler. It's already complicated, and even with these tricks, it's not going to be really simple. The first thing I'm going to notice is that this Ix here is going to be divided to this current and this current, right? One of them is GMV pi. Let's call this other guy I1, right? And well, let's call this guy I2. Well, what I see is that this I1 and I2 come here and they get added up again. So I can say that the current here is also Ix. So I don't care what is I1 and what is I2. I know that they're going to be adding up again here at this node. Therefore, here I have Ix again. Why is that important? Because now I can actually write the voltage at the node P as Vp being equal to Ix times whatever resistance that is at the P, between P and ground, which is Re to ground and R pi to ground. And they're in parallel, so it's going to be Ix times Re in parallel with R pi. Okay, so that's step one. Maybe I should have written this here. So Vp is equal to Ix times Re in parallel with R pi. Now, let me erase that. Okay, now I noticed that V pi, the way it's defined, is basically negative of Vp, because Vp is from this point to ground, V pi is from ground to this point, right? Just note the positive and negative terminals of V pi, right? So from here, I can say that V pi is just negative Vp, so it's going to be negative Ix times Re in parallel with R pi, okay? Now, the next thing I'm going to do is that I'm going to write a KVL from here all the way to here, and then going to V pi and then ground, okay? So it's going to be plus Vx minus R naught times I1 plus V pi is equal to 0. Okay, and then I can say that Vx is going to be equal to R naught I1 minus V pi. And then I1 is really using KCL. I can say that it's basically Ix minus I2, I2 being GM V pi, so it's Ix minus GM V pi. Then minus V pi, and that's how I get this expression. So Vx is equal to Ix minus GM V pi times R naught minus V pi. And now I'm going to replace V pi with what I had here. So I get Ix plus GM, two minuses kind of cancel out each other, plus GM Ix times, so this is really negative V pi times R naught, and then again, this is negative V pi. And two negatives cancel each other, that's why I have a positive here, okay? Now, from here, I have everything based on Vx and Ix, so I can write R out. This is really Vx over Ix from the expression that I had from here, okay? Now, once I write R out, I try to simplify things. So I can say that 1 times Ro, R naught, so I have this, I'm going to break this out, so it's going to be R naught plus GM Re in parallel with R pi times R naught. And then I see that I have an Re in parallel with R pi here, so I factor them out, so I get Re in parallel with R naught times GM R naught plus 1, and then I have this R naught in the beginning, so I add it here. Okay, the last thing I do is that I notice that GM R naught is going to be really, really big number, so plus 1 is just, I can just replace it with GM R naught, so I get this expression, and then from there I take out R naught. It's going to be R naught times 1 plus GM Re plus in parallel with R pi. Okay, so maybe the biggest lesson is that when you bring the early effect into the picture, it's just going to get really, really complicated. But at the end of the day, you get an R out that is much bigger than what we had before. So with a normal common emitter amplifier, the resistance looking into the collector was just R naught, right? Now I have R naught times a huge expression that is basically this Re in parallel with R pi. Let's say it's in the order of, like, I don't know, a few hundreds ohms to 1 kilo ohm, typical numbers, times GM. It's going to be something, imagine that there wasn't any Re. So GM R pi was in the order of beta. So you can imagine that this expression inside the bracket is going to be in the order of 100 or something. So we're increasing this resistance by a lot, right? Is that really bad news? Because we know that we want our out to be very small, and this tells us that our out is going to be really, really big, right? We are increasing it by a factor of 100 or something, right? By 2 orders of magnitude. In reality, it doesn't really matter much, because remember, we haven't, with any kind of a common emitter amplifier, with or without degeneration, I have this RC up here to VCC, right? And whatever I have here at R out is going to be in parallel with RC. Remember, this RC appears here, right? So whatever I have as R out looking into here is going to be in parallel with RC. And RC's values, remember from the examples that we have seen, are in the order of 1 kilo. So if you have an R naught that is, I don't know, 10 kilo, then you know that RC in parallel with R naught is going to be 10 in parallel with 1, so you're going to get a 10 over 11 kilo, so a little bit less than 1 kilo, right? Now imagine this R naught is actually increased by a factor of 100, so instead of 10 kilo ohm, you have not 100 kilo ohm, but 1 mega ohm, right? So now RC, if R naught becomes 100 R naught, with the emitter degeneration, then RC in parallel with 100 R naught is going to be now, well, 1 in parallel with 1000, so you get 1000 over 1000 plus 1. So a little bit less than 1 again, right? So instead of 1 kilo ohm, like basically with a normal common emitter, your 1 kilo ohm would have been, I don't know, 950. Now it becomes 999, right? Doesn't really matter. It's not that big of a deal. It's not like that dramatic change that we thought it's going to be with like basically this expression. So at the end of the day, we need to know the expression, but at the same time, when comparing the common emitter amplifier, the normal common emitter gain stage, and the gain and the common emitter with degeneration, in terms of R out, at least we know that as long as we have some sort of a resistance in the collector, the R out is not going to be that different. But if that resistance would have been changed by some like current source that has an infinite resistance in it, or infinite output resistance, then things would have been different. Then this would have been a really, really bad news. Okay, so these are just basically some sort of a kind of practical perspective that I wanted to actually communicate to you. At the end of the day, what we want to learn from this slide is how to calculate the output resistance. What's the expression of the output resistance of a common emitter with degeneration, so that you know it and you can actually use it in your design questions or analysis questions.